What is the material of the 21st century?
Graphene has revolutionized the world of chemistry, physics, material science, even biology. In 2004, Game and Novoselov proved that it was possible to exfoliate a bulk crystal of graphite, obtaining one single layer, one atom thick, that name it as graphene. They observed that there are amazing properties when electrons are confined in two dimensions and when a large surface area is exposed.
But graphene is not alone. There are many elements in the periodic table exhibiting layer structures that can be isolated into monolayer nanosheets, and even a larger number of multi-elemental materials that can be exfoliated, exhibiting wonderful properties.
For example, we can find from semiconducting to superconducting materials, from diamagnetic to ferromagnetic 2D layers. And also we can observe a broad spectrum of mechanical and optical properties.
And from the chemical point of view, this is also very interesting because we have some materials that are almost inert and other ones that are extremely reactive, from the redox point of view and also from the catalytic point of view.
But how can we obtain one real 2D layer? There are two main approaches, the bottom-up approach and the top-down approach. In the top-down approach, we can follow dry methods or methods in solution.
From the bottom-up perspective, we have also dry approaches and chemical approaches. From the dry point of view, we can use chemical vapor deposition or molecular beam epitaxy, for example. And from the wet chemical approach, we can use synthetic protocols.
In the most simple top-down approach in solution, we use mechanical forces in order to separate the layers that are held together by soft electrostatic or Van der Waals interactions in the bulk crystal. For example, by using a sonicator chip, we introduce it inside a solution and we disperse the layers. But this is very important to pay attention to the solvent that we choose that will help us to separate the layer and make them stable in the suspension. And also, sometimes it will be necessary to add other molecules, for example, as surfactants. When we obtain the dispersions, we have different sizes, and we use centrifugation to separate them and choose the thinnest ones. When we obtain a dispersion of these nano layers in the solution, we can observe the Faraday-Tyndall effect due to the fact that these units have the sizes close to the wavelength of the incident light.
One interesting strategy is the intercalation. The intercalation chemistry allows to diminish the interaction between layers in Van der Waals materials, increasing the interlayer space, minimizing the interaction, and facilitating in the presence of the appropriate solvent of the exfoliation of the material. But this can be also used in layer hydroxides, for example, which are not Van der Waals materials, in order to minimize also the interactions by introducing organic molecules. This is also reflected in X-ray diffraction pattern, in which the peaks related to the pillaring of the structures can be shifted to lower 2 theta values. For working with the reductive route, we have to prepare our materials inside a glove box in which no oxygen and water is present. First of all, we introduce the materials making several cycles of vacuum and pumping with argon. Afterwards, we are going to intercalate our materials, for example, with alkali metals, increasing the interlayer space and minimizing the Van der Waals interactions. Then we will choose an appropriate solvent in which our material can be dispersed, getting exfoliated nanosheets. In contrast to the top-down approaches, in which we don't have a precise control of the dimensions and the thickness of the materials, we have bottom-up synthetic protocols, in which by starting with molecular precursors and playing with the temperature, with the solvents, and with the atmosphere during their reaction, we can precisely control the dimensions of the particles, the thickness, obtaining a large number of identical nanoseeds. One example of these chemical approaches is the hot injection colloidal route. This can be used for the synthesis of layer perovskites or 2D pnictogens, which are based in the elements of the group 15 of the periodic table, like phosphorus, arsenic, antimony, and bismuth. A key aspect of the wet chemical approaches is the functionalization. We can use this in order to improve the solubility of the layers, or in order to modify the physical properties, also for the creation of hybrid structures. For this, we can use a wide variety of molecules, and this will allow us to modify the properties at will. In 2D materials, a very useful characterization technique is the transmission electron microscopy. In this machinery, what we need is to prepare the sample in copper grid, just depositing a drop of our suspension, letting them dry on the surface of the grid, and then introducing this holder inside the microscope. Inside the column, we have a strong vacuum. And then, when we switch on the electron beam, we will be able to observe the morphology of the material, but also the crystallinity, even with atomic resolution. And with different spectroscopies in situ, we can analyze the chemical composition. And with the electron diffraction, we have information of the crystallinity in a single flake.
Sometimes we need to go deeper in the inspection of our 2D layers, and then we need to take our colloidal suspension and put the layers on a surface. For this, it's really useful to use a spin coating. That is an easy way to disperse the layers on a substrate, eliminating the solvent. Once we have our substrate with the dispersed layers on top, we can inspect them on the optical microscope. But the sizes are small and sometimes it's difficult to find them. However, it is still useful to try to identify the best places on the substrate that will be further studied by atomic force microscopy. Thanks to the atomic force microscopy, we can get three-dimensional images of our flakes, getting information of the thickness of the layers. In the atomic force microscope, a tip scans the surface in order to obtain a topographic image and other interesting properties. In this way, we can get a three-dimensional profile of our 2D layers, being able to measure their height and morphology.
Another useful characterization technique is X-ray photoelectron spectroscopy. Here, what we analyze is the very surface of our 2D material, obtaining information of the chemical composition and, even more interesting, about the oxidation state.
Raman spectroscopy is a very useful technique in order to get information about the chemical structure of our layers. In the spectra, we identify different peaks, and these peaks give us information about the nature of our material, the phase that it presents, and even about the thickness that these layers have. We can get simple spectra in a position, and we can also do mapping of the surfaces.
One of the main problems in 2D materials is scaling up the production of the layers. For this, the wet chemical approach is one of the best options. Indeed, using synthetic protocols, we can scale up to the limit of kilograms the synthesis of two-dimensional layers. In order to illustrate the possible application of these materials, we are going to focus in one of the hottest topics in research: energy storage and conversion. For example, there are two-dimensional materials that are excellent electrocatalysts, and they can be used to split water in oxygen and hydrogen. First of all, we need to analyze what is the kinetics of these materials. For this, we can use rotatory electrodes. Afterwards, we have to prepare chemical cells in order to analyze what is the overpotential that we need to apply for splitting water into oxygen and hydrogen. Other application that is gaining a lot of attention during the last years is energy storage. For this, one of the possibilities is to create a prototype. For example, we can deposit our 2D materials combined with some binders and creating some small batteries like coin cells that can be useful to demonstrate that we can apply these materials in bigger electrochemical storage devices.
As you have seen, 2D materials is an exciting topic that has shown amazing results in the last few years.
But there are still many open questions and challenges to solve in physics, chemistry, engineering, in order to make closer to the society these materials.
Flatland is waiting for you.